In this video, we will prove the differential privacy of the exponential mechanism. The proof is quite straightforward, although explaining the setting is a bit cumbersome. Recall that we defined a utility function u from the set of databases times the set of responses to R, and that the exponential mechanism returns a response R for database X with probability exponential in epsilon times u of x and r divided by delta u, where delta u is the largest utility variation between neighbor databases x and y for all responses R. In a previous video, we claimed that such an exponential mechanism is epsilon differentially private. Now, before proving the theorem, I'm going to prove a simple lemma. The lemma says that if alpha s divided by beta s is at most gamma for all values of s, then the sum of the alpha s divided by the sum of the beta s is also at most gamma. This is quite easy to prove. Indeed, the assumptions allows us to say that alpha s is going to be at most gamma times beta s. And so when we take the sum over all alpha s, this is at most the sum over all gamma beta s, which is at most gamma times the sum of beta s, and thus the ratio of the sums is going to be at most gamma. Now we can move on to the proof of the theorem. To prove the theorem, let us define alpha s, which is going to be the exponential of epsilon divided by 2 delta u times u of y and s, and we're going to define beta s to be the exponential of epsilon divided by 2 delta u times u of x and s. Then if we take the ratio alpha s divided by beta s, then we have a ratio of exponential functions, which is the exponential of the difference, which is thus exponential of epsilon divided by 2 delta u times u of y and s minus u of x and s. And we know that this difference is at most delta u by definition of delta u. So this is at most exponential of epsilon delta u divided by 2 delta u, which is epsilon divided by 2. And similarly, we know that beta s divided by alpha s is also at most e to the epsilon divided by 2. Now, let's consider any response R. If you take the ratio of the probability that m of x is equal to R by the probability of m of y being equal to R, this is going to be equal to beta R divided by the sum of the beta s divided by alpha R divided by the sum of the alpha s. And this is equal to beta R divided by alpha R times the ratio between the sum of the alpha s by the sum of the beta s. Now, using the bounds we found earlier, we know that beta R divided by alpha R is at most e to the epsilon divided by 2. And by using the other first bound we got earlier and the lemma that we've proved, we know that the second term, the ratio of the sums, is also at most e to the epsilon divided by 2. If we combine it all, we obtain an upper bound of e to the epsilon divided by 2 times e to the epsilon divided by 2. This is e to the epsilon QED.